Hello, in today's video, we're gonna do exercises based on Laplace transforms, inverse Laplace transforms, and solving differential equations with Laplace transforms. There's gonna be a lot of examples here, so brace for them. Now notice that I wrote here a lot of the things that we proved in our previous video. I have Laplace transform of 1 of the cosine of the sine of the exponential, the first shift theorem, the second shift theorem, the Laplace transform of the heavy side, the Laplace transform of the delta, the Laplace transform of the integral, the Laplace transform of the derivative, and the derivative of the Laplace transform. We're going to be using this in our exercises. Now, notice that I didn't write here one of the expressions that we actually found using the definition in our previous video. I didn't write the Laplace transform of t, right? And the reason is that we're going to be doing as a first exercise, finding the Laplace transform of t to the power n, where n is a positive integer. So, in particular, n equals 1 is the Laplace transform of t. You remember what it was? The result was 1 over s squared, remember? Well, let's find it without using the definition. You don't need to use the definition to find them, actually. Why? Because we're going to use the Laplace transform of 1 and the theorem that we call the derivative of the transform. How? Well, you see that the Laplace transform of Tn is the t to the n is the same as the Laplace transform of t to the n times 1. So it looks like this, only that f of t is just 1. Oh, that's easy then, because on the other side, I use the Laplace transform, the derivative of the transform, and I get dn times dsn, right, of the Laplace transform of 1. And that's pretty easy, because this is minus 1 to the power n, nth derivative of 1 over s. All right? Okay, so the first thing that we're going to do, so this is an expression that works for any of them. We're going to find a general expression. We're going to do that derivative, and we're going to do all this minus 1 to the n in a simpler expression. All right, so as an accessory calculation, let's compute the different derivatives of 1 over s, because we're going to need them, right? So ds of 1 over s, the first derivative, that is minus 1 over s squared. All right, nice. D squared, ds squared of 1 over s is ds of minus 1 over s squared, right? And that is minus 2, and minus times minus is plus, so it's 2 divided by s cubed, right? Okay. Now, the third derivative is 1 over s is the ds of the second derivative, and the second derivative I just computed, which is 2 over s cubed. All right, so that means that I get a minus 3, so I'm going to write like that, minus 3 times 2, the 2 comes out if you want, and this is 1 over s to the 4. Ah, I start seeing a pattern. Do you see it? Let's see. This thing is the fourth derivative, this is the fourth one, of 1 over s is the derivative with respect to s of this thing. Minus 3 times 2, 1 over s to the 4. Right. The 1 over s to the 4 gives me minus 4, 1 over s to the 5. The minus and the minus cancels, and I get 4 times 3 times 2, 1 over s to the 5. Huh, s and 5, you know how they conspire against my handwriting. All right. All right, so look what nice pattern we have. We get n1 minus with a minus, plus, minus, plus. Nice, we get so in general, the nth derivative, n times, right, with respect to s of 1 over s is minus 1 to the n. You see the pattern? The sign alternates. Is there when n is odd. 1, 3, 5, they would have a minus 1. And what do I get here? 4 times 3 times 2 times 1. Ah, that is 4 factorial, that thing. That thing here is 3 factorial. That thing here is 2 factorial. That thing here is 1 factorial. Aha! So what I get as a coefficient is n factorial divided by s to n plus 1. There you go. This is the nth derivative of 1 over s that we computed inductively. You know, doing 1, 2, until we do it. You see how the pattern emerges? If you don't see the pattern, then you will be forced to do another element, and then you will get, when you do it again, you will get minus 5 times 3 times 2. Minus 5 times 4 times 3 times 2. 1 over s to the 6. And then you see the factorial building, the sign alternating, and the n plus 1 in the exponent. All right? Okay. So now that we know that, we can substitute here, and then we get that the Laplace transform of t to the n is equal to minus 1 to the n. And then I substitute this by the expression. Minus 1 to the n factorial s n plus 1. Minus 1 to the n times minus 1 to the n is minus 1 to the 2n, which is 1 to the n, which is 1. So this thing is just 1. When n is even, is 1 times 1. When n is odd, is minus 1 times minus 1. So it's just a 1. So this thing is actually n factorial divided by s to the n plus 1. How nice! So we found it. If this thing is the Laplace transform of t to the n, nice thing to remember in your toolbox, right? We just check that for n equals 1, the Laplace transform of t is when n is equal to 1 in this expression, so that is 1 factorial divided by s 1 plus 1, so it's 1 over s squared, which is what we found actually through the definition. So it's compatible with what we found before. This is the expression of the Laplace transform of t to the n. Exercise solved. All right, let's do another exercise. All right, second exercise is, well, find the Laplace transform of this function g of t. All right, so how do we operate? Well, we know that capital G of s, which is of course the Laplace transform of g of t, would be equal to, the Laplace transform is linear, so it's the Laplace of the exponential of 3t, 3t, plus the Laplace of the cosine of 6t, minus the Laplace transform of e to the 3t cosine of 6t. All right, where I use linearity of the Laplace transform. Wonderful. So, pretty easy stuff. Let's see. What we have here is, for the first one, let's write it. G of s is equal, first term, let's call this term 1. Is the Laplace transform of an exponential? I just looking at that, this is like very stupid work. Look at it at the table. Oh, it's minus 1 over s minus a. A here is 3. So very easy. It's 1 over s minus 3. This is term 1. All right, cool. Term 2. This is a cosine. Well, again, very brainless. Find in the table the Laplace transform of the cosine. We've already done the hard work. That would be s divided by s squared plus a squared. Right, and then 3. Well, this is 2. The only non-trivial, I mean, to say something, is this one. But we realized quickly that it's the product of an exponential and a cosine. So it's going to be the first shift theorem that tells me when I have an exponential multiplying a function, is the Laplace of the function as if there were no exponential but shifted by a. Okay, cool. So the function is the cosine of 6t. So it would be the f, if you want, let me just write it here. This would be the Laplace transform of the cosine of 6t, but shifted, evaluated at s minus 3. Okay? So maybe I'll write it in small so you don't confuse this with a product. Evaluated at s minus 3. Okay? Well, I don't need the bar. Let's check the notation. Let's do it like that, as s minus 3. All right, so I substitute it and I get, well, 1 over s minus 3 plus s divided by s squared plus a from before. And now here, I get the cosine. The cosine would be s divided by s squared plus a squared. Now, whenever I see an s, I write an s minus 3. So this thing is s minus 3 divided by, and then s minus 3 squared plus a squared. And a here is 6 squared, so 36. All right, so that's it. This is g of s. Exercise solved. Very simple. Don't worry, we'll get to complicated ones. Still, we're gonna keep it simple for a while. Let's do another. I can actually do another in this very same board, all right? So I can do the Laplace transform. I find the Laplace transform of, let's call it h. H of t is t squared sine of 2t. Let's do that one. All right, well, we know that the Laplace transform of h of t, we're gonna call it, you remember, h, capital H of s, all right? So this thing is the Laplace, well, I'll write it, is the Laplace transform of t squared sine 2t, for sure. Now, we realize very quickly that we can use the Laplace, the derivative of the transform for this expression. I know what the Laplace transform of the sine is, and I have a t and multiplied, so this thing is gonna be, using the theorem, minus 1 to the 2, okay, t squared, second derivative of f of s. F of s, this is small f of t here, right, in this theorem. So f of s, f of t is sine of 2t, so capital F of s would be the transform of the sine. So it would be a here is 2 divided by s squared plus 4, 2 squared. Okay? We just need to perform that derivative. So let's do it. Let's do 1. Minus 1 to the 2 is 1. So this is ds. And then I do first the derivative inside. So this one's going to be minus 4s divided by s. This is an s. Remember the typical confusion between 5s and s's? In case of doubt, it's an s. A 5, I will be very explicit when I do a 5 and put 35 in it. All right, anyways, s squared plus 4 squared. That's the first derivative of that guy. Now we do the second derivative. I'm gonna expand this, okay, just for fun. This is dds, and then minus 4s. Expanding that, I get s to the power of 4 plus 8s squared plus 16, right? And then the derivative of that is 12 s to the 4 plus 32 s squared minus 64 divided by s to the 4 plus 8s squared plus 16 squared. I can simplify this a little bit because this can be easily factored. I mean, in general, you would like to simplify as much as you can. I mean, if you're working from home, you can add Wolfram Alpha if it's simplified enough. So yeah, you have to simplify. So simplifying, do it yourself. Don't use Wolfram Alpha. Just use Wolfram Alpha to check. Okay. Anyway, so if you simplify, you get s squared plus 4, 12s squared minus 16 divided by s squared plus 4 to the power of 4. This is a perfect binomial. All right, so this cancels, well, not all of it, sorry. S squared plus 4 to the power of 4. This one cancels with one of them. So what we get is finally, so h of s, it's capital H of s, is equal to 12s minus 16 divided by s squared plus 4 cubed. And there you go, another exercise solved. Not difficult, just a bit longer. And so you practice arithmetics a little bit and derivatives. All right, let's do another exercise. So we've seen that to compute Laplace transforms, we don't have to go to the definition usually. For the purposes of what we do in this course, we can get away with all those theorems that we proved, which is nice. Now, let's do the inverse Laplace transform of this function over here. So I give you a function in the S domain, in the Laplace domain, okay? And I want to, in the time domain, the t domain, I want to invert the Laplace transform. All right. So I know that I'm looking for g of t would be the inverse Laplace of, well, 86s minus 78 divided by, how nice of me, I already gave you this factorized in its roots, s minus 4, and then 5s minus 1. Notice that I try to distinguish the 5s really well from the s's, okay? All right, so this is a task for simple fraction decomposition. So let's do it. All right, first, so GS is this guy and this guy, right, the same, but we can write it as three simple fractions. A divided by s plus 3 plus b divided by s plus 4, minus 4, right, plus c divided by 5s minus 1. Wonderful. So I'm gonna do it. I mean, at some point I will not do full detail. I'm gonna keep telling you, but then I don't do it. Anyway, I'm gonna do it full steps, right? Except for solving the linear systems. Usually, those ones I'm gonna leave to you. But I'm gonna do full steps here, just so you know it's easy for you, or at least you have some more practice. But there is something that you should be able to do yourself. Finding the simple fraction decomposition is previous course material. Anyway, I'll do it. So I take common factor and I get a that multiplies s minus 4, 5s minus 1 plus b that multiplies s plus 3, 5s minus 1 plus c that multiplies s plus 3, s minus 4. There we go. And there's a common denominator, which is the product of 3s plus 3, s minus 4, and 5s minus 1. All right, so we know that this numerator has to be equal to this numerator, the denominator is the same, so we set up an equation. That means these two things have to be equal, and that means that, would it fit here? Maybe not. I'll write in the next line. That means that a times s minus 4 times 5s minus 1 plus b s plus 3, 5s minus 1 plus c s plus 3 times s minus 4 equals, that's on the left hand side, which is this. Right hand side is 86 minus 78. Now, of course, you can always do what we will do in most of the cases, which is expand this and equate 86s minus 78. Right. So typically what we do is expand this and equate all the coefficients of s squared on the left with all the coefficients of s squared on the right. All the coefficients of s on the left with all the coefficients of s on the right. All the independent terms on the left with all the independent terms on the right. But here, there's a much faster way to do it. We can choose particular values of s's, right, that cancel two of the terms and leave only one unknown. So for example, if I take the particular case s equal minus 3, then this becomes the following. So s equals minus 3 cancels this term and cancels this term, leaves only that one. So it's minus 7 times minus 16 a equals, and then on this side with s equals minus 3, after you do the product, you get minus 336, right? So if you divide this thing, you get that a is equal to minus 3. Very easy. Arithmetics. Calculators do it for you, computers do it for you, I do it for you. Arithmetics. All right. So, fine. Then now let me take one that cancels this and that. So s equals, or no, maybe let's cancel this a and b. So S equal 1 over 5. That cancels this term and cancels this term, leaves only C. So I get 16 over 5 times minus 19 over 5, right? Coming from this one and this one. When you substitute 1 over 5. Times C equals, and on the other side, we get minus, a total of minus 304 divided by 5. When you do this sum, 86 over 5 minus 78, that's what you get in the end. All right, so you can solve for C. Actually, it's very easy. The result, C is 5. Very simple. Arithmetics. Just divide. All right. Finally, we can take S equals 4. And S equals 4 cancels the first term and the last term, and I'm left with this one. That would be 7 times 19, like 7 times 19 times B. And on the right hand side, with S equals 4, I get 266. And that allows me to solve for B. B is equal to 2. Wonderful. Now, having found the coefficients of the simple fraction decomposition, I know that because of this or that, I know, well, I don't write that arrow. I know that GS now, I write as the simple fractions, is minus 3 divided by S plus 3, plus 2 divided by S minus 4, plus 5 divided by S, 5, S minus 1. All right, wonderful. So now we need to invert the Laplace transform. Remember, we know that G of t is the inverse Laplace of all of that, G of S. And doing that, we get that G of t is, of course, and then let's write like that. Let's take the factors out, minus 3 Laplace of 1 over S plus 3, plus 2 Laplace of 1 over S minus 4, plus 5 Laplace inverse, of course, sorry, my bad. Inverse Laplace. I'm taking inverse Laplace. Inverse Laplace of 1 over 5 S minus 1. All right. So we need to express them in terms of things that are on the table. Now the first one is really easy. Let's just write these two, and the last one we do the last one, so easy, but just in case, let's do that independently. So that's minus 3, and this is the Laplace transform of the exponential of e to the 3t, right? So the inverse Laplace transform of this is, using this, the exponential of minus 3t, right? Because there's a plus and there's a minus here. Okay, a is minus 3 in this case. Wonderful. Plus 2, and this one is the exponential of 4t, using the same result, the Laplace of the exponential. Finally, this one, we need to write it as, it's going to be an exponential, but doesn't quite look like the exponential, because to have the exponential here, I need to get an s alone, and I have a 5s in there. Well, no matter. What I do here is divide I can, let's say, I multiply by 5, which is divide, if you want, the numerator and denominator by 5. Right, if I do that, I get 5 plus 5, and then Laplace, I'll be very explicit with the steps because it's the first time we do it. 1 over 5 divided by S minus 1 over 5, right? I divided numerator and denominator by 5. Okay, cool. Now I can take the 1 over 5 out, and I get minus 3 e to the minus 3t, plus 2 e to the 4t, plus 1 over 5 cancels the 5, inverse Laplace of 1 over s minus 1 over 5. And that thing now is definitely in the exponential form. This is e to the 1 over 5t. All right, so finally, the final result, let me just write it here. G of t, it's equal to minus 3 e to the minus 3t plus 2 e to the 4t plus e to the t over 5. And that's the result. Again, for this one, I used the Laplace of the exponential and inverted it. Apologize I didn't write the minus 1 at the beginning, but other than that, that's the result. Another exercise solved. Another equation saved. All right, let's do more. All right, so we need to find the inverse Laplace transform of this function here. This is more difficult than the previous one, and we will see how and why. Okay, so the first thing we need to do is a simple fraction decomposition as usual. If we do a simple fraction decomposition, I know that f of s should be equal to a divided by s minus 6 plus bs plus c, right? It's a complex root, an imaginary root in this case, divided by s squared plus 11. Wonderful. So what we do is, again, common denominator, and we find that f of s, maybe I'll try to save space, not that for this one we'll need a lot, but f of s, right, would be equal to, then in the numerator, I get a multiplying s squared plus 11 plus bs plus c, that multiplies s minus 6 divided by s minus 6 multiplying s squared plus 11. Now this thing has to be equal to that thing, that means the numerator has to be equal to this numerator. That gives me the following equation. A that multiplies s squared plus 11 plus bs plus c that multiplies s minus 6, it's equal to this is an s of course, right? Always an s, to minus 5s. All right. So we see that actually, oh, sorry, forgot the parentheses. My bad. We see that there's one easy case. One easy case is when s is equal to 6. If s is equal to 6, I get automatically an equation for a. All right, let's do it. Let's do that case first. So for s equals 6, the equation that I'm left is 2. Well, on the right hand side, well, let's do the left hand side first. It's 47a. Right, this is 6 times 6 plus 11, so 47 times a. This one's 0 equals to 2 minus 30. And you can solve for a, and you get that a is equal to minus 28 divided by 47. That's the value for a. All right, now we need to find b and c. How do we do that? Well, for this one, there's no other option. I mean, you could choose an imaginary value. I mean, you could, in principle, cancel this one with an imaginary yes. We're not going to do that. People tend to fail dramatically at this level for some reason. So we'll expand the system and create a system of equations, right? If we expand the system, we get a s squared plus 11 plus 11a, sorry, plus bs squared minus 6bs plus cs minus 6c equals to minus 5s. All right. Now, what we do is, again, the typical thing, we equate the coefficients of s squared on the left equals the coefficient of s squared on the right. Coefficients of s on the left equals coefficient of s on the right. Independent terms on the left equals independent terms on the right. So let's do that. The equation for the coefficients, maybe I'll save the space, I'll put it here. Well, yeah, I'll put it here and I erase. The coefficients of s squared are on the left, a plus b. On the right, there's no square, so 0. The coefficients of s to the 1 are, what multiplies s in here? I have minus 6b I have plus c on the left, so minus 6b plus c, and on the right, minus 5. And then finally, the independent terms, the coefficients of s to the 0. And that gives me 11a on the left minus 6c, so 11a minus 6c, and on the right 2. Alright, this is a system of equations. Actually, we already know a. We can substitute. A is equal to minus b, so we get very quickly that b is equal to 28 divided by 47. And then finally, c gives you minus 67 divided by 47. Alright, so those are the independent, the simple fraction coefficients. So let's write s, knowing this, f of s in terms of the simple fractions. I'm going to erase all this. Remember the coefficients. They will appear in the simple fraction decomposition, but let's do that quickly, and because we need to clear the board. We have only one board. So we get the simple fraction. Those are the coefficients a, b, and c that we obtained right before, and those are the simple fractions. Now, of course, if we want the Laplace transform, the inverse Laplace transform of f of s, which is, of course, what we want, f of t, f in the time domain, then the inverse one. Okay, don't forget the minus 1 on time. Okay, then we take inverse Laplace transform of the right hand side. So this thing is going to be minus 28 divided by 47 inverse Laplace of 1 over s minus 6. That's easy. Okay, next, plus 28 divided by 47 inverse Laplace of s divided by s squared plus 11. There we go. Now, finally, minus 67 divided by 47 inverse Laplace of 1 over s squared plus 11. All right. Wonderful. So, let's see what we have here. Let's identify terms. Now, the first one looks like an exponential. Let's write them here. Let's just number them. Maybe I'll use blue for that. I call this one 1. I call this one 2. And I call this one 3. Now, then f of t, it's equal to minus 28 over 47, and then the term 1. The term 1 is clearly the inverse Laplace transform of the transform of an exponential, where a is equal to 6. So this thing is e to the 6t. Very easy. That's term 1. All right. The next one, term 2. Okay, so 28 divided by 47. Now, what is this? Well, clearly, this looks a lot like the cosine. So it looks like a cosine where a is square root of 11. So that a squared is 11. All right, so this thing is the cosine of square root of 11 times t. All right, now the last one. The last one almost looks like a sine. But to be a sine, I should have an 11 over here, right? No, not quite, no. I should have a square root of 11, because if this is a square, this should be a. So if this is 11, this should be square root of 11. I need a square root of 11 on top in the numerator, and I don't have it. But I can put it in. How? Well, dividing and multiplying by square root of 11. So what I'm going to do is minus 67 divided by 47. Then I divide by square root of 11 outside, because you know that can come in and out of the inverse Laplace transform because of linearity. And then I multiply by the square root of 11 inside. So what I did, this is the same, right? What I did is, all right, this thing, what I do is, oh cool, I'm gonna multiply by square root of 11, and I'm gonna divide by square root of 11, s squared plus 11, inside the inverse Laplace transform. And then what I did is just times, right? and then what I did, I took this one out. Okay? Hopefully clear. Wonderful. So in this form, I know what it is. In this form, it's certainly the sine of AT, where A is the square root of 11. So let's write the final result. F of t is equal to minus 28 divided by 47 e to the 6t plus 28 divided by 47 cosine of square root of 11t minus 67 divided by 47 1 over the square root of 11 the sine of square root of 11t. And that is the solution to this exercise and another exercise solved. All right, let's do another. There's so much to go through. The secret to learning is practicing. Didn't work, sorry, second try. All right, let's find the inverse Laplace transform of this function here. 25 divided by, that's Tarifa super big. 25 divided by s cubed multiplying s squared plus 4s plus 5. Now, this one is the most difficult that we've done so far, and we'll see why. I added here to our toolbox the formula that we proved at the beginning of the video, the Laplace transform of t to the n, which is n factorial divided by s plus 1. All right, simple fraction decomposition. In this case, this thing has complex roots. So in this case, the decomposition is going to be a to the power of s from the s cubed, right? Sorry, a divided by s plus b divided by s squared plus c divided by s cubed, okay, plus bs plus e divided by s squared plus 4s plus 5. All right, so if you do the simple fractions, which is again multiply, you know what the method is, you get the following system of linear equations. You get with the coefficients of steps. Write this with common denominator. That will get, for example, a will multiply by s cubed, will multiply by s squared plus 4s plus 5, etc. Okay? After you do that, you get the following system of equations equating. Then after you do that, you equate the result of common denominator here with this result. The denominators are the same, so that means that the numerators are equal to 25. And that gives you a system of equations. And the system of equations comes from the different coefficients of s, of different powers of s. Now, so the coefficients, let me write the system. I'm not going to do all the time this long calculation. The video will take forever. So you do that one, but I'll tell you the system of equations you get. The coefficients of s4, s to the 4 are a plus b. Kind of easy to see that you would get an s to the 4 from these ones, right, with the a, right? You need 2 powers extra of s, and then you get another 2 powers from here, you get an s to the 4, anyway, whatever. You do it, please. A plus b, and on the right is a 25, so there's no power of s to the 4. The coefficients of s cubed gives you 4a plus b plus e. On the right also there's no s cubed. The coefficients of s squared will give you 5a plus 4b plus c equals 0. Then the coefficients of s to the 1 is 5b plus 4c equals 0. There's also no s on the right hand side. On this side, I mean, there's only a 25, so now it will appear on the right hand side. The coefficients of s to the 0 give me 5c only. The only c will get a coefficient of s to the 0 in here. Comes from the 1 multiplying the 5 in here, right? And that one is equal to 25. So this is very easy to solve, perhaps slightly tedious, although, a computer does it for you in a second, the time that you take to input the coefficients. A is equal to 11 over 5, B is equal to minus 4, C is equal to 5, trivial from here, D is equal to minus 11 divided by 5, and E is equal to minus 24 divided by 5. So those are the coefficients of the simple fraction. Please, if we practice, we've done like 10, well, I don't know if 10, but we've done a number of the order of 10 in the course, full detail. This almost full detail, except for the fact that I didn't multiply the denominators to get the common denominator. please do it and check that you get that. It's good practice. Alright, so what we're going to do now is write the simple fractions. Let me erase the board and start from, because we're going to need all the space. So I wrote here the simple fraction decomposition with these coefficients. Remember that actually A was 11 divided by 5, and I wrote this is not a 5, this is an S, remember? So I took a common factor 1 over 5 from all the coefficients, so that's 11 divided by 5 over S, and 1 over 5 is out. I did that for all the coefficients because it becomes much easier. So that means that g of t, which is of course the inverse Laplace of capital G of S, it's equal to 1 over 5 that factors out, and then the 11 times the inverse Laplace of 1 over S minus 20 inverse Laplace of 1 over S squared. Okay? Plus 25 inverse Laplace of 1 over S cubed. Alright? And minus inverse Laplace of 11s plus 24 divided by S squared plus 4s plus 5. Alright? Now let's do the easy ones first. These are easier, and this one is a bit more difficult. So let's do that. Now the first one, let's go in order. G of t equals 1 over 5. Now multiplies. Now the first one is easy. The first one is 1. So it's the Laplace transform of 1. So this thing is the Laplace transform of 1. So the inverse Laplace transformation is 1. So this is just an 11. There we go. Wonderful. Minus 20. What is this? Oh, this one is the Laplace transform of t. So very easy. So it's the inverse Laplace transform of 1 over squared, that's t, so minus 20t. What about that one? Well, let's see. That one, we have the formula here. Remember, the Laplace transform of t squared, it's equal to 2 factorial, which is 2s cubed. Right. That's not quite what we have here. To get t squared, I need a 2 in there. So I need that this thing, what I can do is multiply inside by 2, divide outside by 2. So this thing is equal to 25 divided by 2, inverse Laplace of 2 over S3, S cubed. And that thing is t squared. The Laplace transform of t squared is 2 over S cubed. Alright? So we write that. This is plus 25 divided by 2, t squared. Important. Some people make the mistake of writing t squared directly here. No, there's a coefficient. You need the 2 in there. You need the 2 in there. So you need to put it and divide outside. Alright. Now, the more difficult one. What is the trick for that one? What does it look like? So this one looks like perhaps this is going to be a sine or a cosine or both, right? Maybe the s divided by some quadratic thing looks like a cosine. The independent term divided by the quadratic thing looks like a sine. Right. The first thing we need to do is to actually write this thing as some square plus something. So what is the monomial? I need to write this thing as some square plus something squared plus a constant. This particular one, this denominator, so let's just write it here, right? I mean, maybe let's take, let me just write it here, just for completeness. L minus 1 of 11s plus 24 divided by, and then this thing is s plus 2 squared. So you look at that, right? And that's what you need. You check that and you say, okay, I want to get the right coefficients for s squared and s. That means that I need something like, this thing is going to be like s plus 2 squared. It's like that, right? I mean, you see that the s squared and the 4s is going to come out right. The only problem is that that gives me a 4, not a 5. See what I mean? I mean, let's see the logic. I want to express this as a square plus something. Okay, this is clearly this thing that I have. Well, it looks a lot like s plus 2 squared, because that gives me s squared plus 4s plus 4, right? That's not quite this one. I'm missing a 1. Okay, fine. 1 plus 1, that is a 5. I get that. You see how I do it? First, I get these two terms, which is easy. I need to get these two terms. I need s plus 2 squared. And the independent term, sure, it will be whatever is left for the 5. How you got it? So this thing is equal to this. S squared plus 4s plus 5 is 1 plus s plus 2 squared. Alright? I'll do it again. So repetition. I want s squared plus 4s plus 5 as I want it as s plus something squared. Perhaps plus something. Right? Because this is the form these things have. Something squared plus something. And then you say first, right, I want to nail this factor 4. To have a factor 4, I need a 2 here. But that makes that I won't fit this one, because that gives me s squared, that's fine, plus 4s, that's fine, plus 4. And I have a 5. Okay, fine. I add 1. That's the way you do it. Hopefully, practice, look at it. We'll do it more time. You'll do it more time when you practice assignments and everything, and you will come to the review sessions to ask me if you have particular questions about it. Now, let me write it here. So this thing is s plus 2 squared plus 1. All right. Now, now that I have that, I need to transform this into something like the cosine and something like the sine. How do I do that? All right. So, first let's see. This thing, I can decompose it into two things. So what I'm going to do is the following. 1 over 5. Oof, looks like SS all the time. 1 over 5. 11 minus 20t plus 25 divided by 2t squared minus inverse Laplace. Now what do I need? Okay, so if I want to have something here like the sine or the cosine, at least for the sine, so what I need here is to have the same coefficient. You see, for the cosine, I need to have s in here. Now the problem is that I have s plus 2 in here. So the thing that is squared in this case is s plus 2. So in the numerator, I need an s plus 2 as well. Okay? I need to put in the numerator the same variable squared that I have in the denominator. In the numerator, I have an s, I need an s plus 2. How do I do that? Well, that's easy. Because what I can do is 11 times s plus 2 minus 2. I added plus 2 and subtracted 2. Plus 24 divided s plus 2 squared plus 1. Alright, now 11 times minus 2 gives me minus 22. Plus 24, that gives me 2. So, wonderful. This thing I can write as 1 over 5. These ones are all the same. Minus 20t plus 25 divided by 2t squared minus. And now I have the inverse Laplace of two fractions. The first one is 11 s plus 2 divided by s plus 2 squared plus 1. Right? And then minus, because it's the same minus here, Laplace transform of 2 divided by s plus 2 squared plus 1. Hopefully you see what I did. What I did is, okay, I was here and I thought, okay, I don't need an s here, I need an s plus 2 to have the same variable in the numerator and denominator to get something that may look like the cosine, perhaps displaced, but the cosine. I need to have the same displacement in the numerator and the denominator. All right, how do I get that? Well, I add plus 2 and minus 2, that's doing nothing. But the nice thing is that I factor 11 s plus 2 in one term, and the other one I shifted, the 11 times minus 2, I shifted to this guy. So what I get in the end is 11 s plus 2 divided by s plus 2 squared plus 1, and then another fraction, because this is a sum of two fractions, right? I can put this 24 in a different fraction, with this 11 times minus 2 in a different fraction. And then it's 11 minus 2 is minus 22 plus 24, 2, divided by the same denominator. Okay, it's looking better. It's looking better. All right. So, what we have here then is the following. This one, we can already see more or less what we have. So the 11 can come out. So let me just write. We have 1 over 5 multiplying 11 minus 20t squared plus 25 divided by 2t squared minus, that would be 11 inverse Laplace of s plus 2 divided by s plus 2 squared plus 1 minus 2 inverse Laplace, oh, I forgot the inverse here, sorry about that, inverse Laplace of 1 over s plus 2 squared plus 1. Alright, now, this thing looks a lot like the cosine. Look at the cosine. The only difference is that instead of an s, I have an s plus 2. So it's a cosine displaced by 2 units to the left. Aha, but we have here the shift theorem that tells me, oh, if you find one that you recognize, like the cosine, the only difference is that it's displaced by some amount, then the Laplace transform is the cosine that you should have had, but multiplied by the exponential of the displacement. So this thing here would be the cosine. What is the value of a in this case? Well, a is 1, right? So this is the cosine of t, only that is displaced by a value a equals to minus 2, because it's summing, not subtracting. So it's e to the minus 2t. Alright? So this Laplace transform is e to the minus 2t cosine of t. And here you can tell this one is very similar, is the sine, is basically the sine, with a equals 1. So certainly is the sine of t, 1 times t. Now, the thing is that it's displaced by how much? By minus 2 units. So exponential of minus 2t. I hope that's clear, but if not, please repeat it. Repeat all the steps, see how I do it, see how I match. I'll do a summary after. Let's write a final result. The final result is that g of t is equal to 1 over 5 multiplying 11 minus 20t plus 25 divided by 2 t squared minus, and now 11 e to the minus 2t cosine of t minus 2 e to the minus 2t sine of t. And that, my friends, is the final result. Another exercise solved. Now, let's summarize, because this one is definitely the most difficult one. It doesn't get more difficult than that in the exercise that you will find. I mean, the other kind of complication will come when we have heavy sides and deltas that we will see in a minute when we solve equations. But you can tell that what I did here is try to make it look like a cosine or a sine, even if displaced. Okay, so when I arrive to here, I automatically say, oh yeah, something s over something s squared plus something, and something without s over something s squared plus something, that's going to be sine and cosine. They're going to appear in pairs. That's super common. Remember when you solve differential equations, sines and cosines appears in pairs. So when you get something like that, suspicion, a sine plus a cosine, it's going to be that. All right. Now, to make it look like a cosine or a sine, I need in the denominator, whatever is squared, what would be the s, only displaced, I need it to be in the numerator as well for the cosine. How do I get it? Well, adding and subtracting whatever's missing. And then I group. This is doing nothing, but allows me to group the 11s plus 2 in one fraction, and then the 11 times minus 2 in another fraction. After doing that, it looks like this, and now it looks like a cosine, oh, maybe even here, right, after taking the factors out. This is a cosine if only instead of s plus 2 was s. Hold on, that's a displaced cosine. So I have a theorem that tells me, oh, if your function is displaced by a, then add an exponential of that a. This one is displaced by minus 2, so add that exponential. This one, same thing, it's the sine, right? A is 1, so it's the sine. It's just displaced by minus 2. Wonderful, so add the exponential of minus 2. And that's it. Again, do it, practice it, you'll do practicing assignments and ask me questions, all right? All right, let's see more exercises. All right, so this problem is solving a differential equation, or look at that. It's like a harmonic oscillator, you see? It is a harmonic oscillator, only that the driving force is not sinusoidal, it's not an oscillatory force, it's a delta. Physically, my oscillator is doing its thing with some initial conditions, so I pull it and start doing its free oscillations, and suddenly, some stupid kid at time equals t equals 9, kicks it. It's disturbing the harmonic oscillator by a kick of 6 units of energy. So the kick is doing, so the kid arrives and goes like, and kicks it really fast. That's what the delta is. Nothing happens, suddenly at some point, a spike, right? Now, what do you expect to happen? I expect to happen that the behavior is discontinuous. It's like doing its thing, oscillating and decaying, or whatever it does, whatever the solution of the homogeneous problem is, right? And then, when the kid arrives, suddenly the oscillator is going to feel an impulse, and it's going to be a heavy side, right? Something that appears suddenly. Something like a heavy side should be in the solution. Because before t equals 9, there's no force, it's free. At t equals 9, somebody kicked it. All right? So let's see what happens when somebody kicks an oscillator at time equals 9 with a very fast kick. All right. To solve this differential equation with these initial conditions, what we do is taking Laplace transform on both sides, as we have been doing. So we get the Laplace transform. Let me write it, right here. The Laplace transform of y dot dot plus twice the Laplace transform of y dot minus 15 the Laplace transform of y equals 6 the Laplace transform of delta t minus 9. All right. Oh, hold on. So gross. Minus 9. There we go. All right, so we know how to write that. The Laplace of the second derivative, we use the Laplace of the derivative that we have here. So the first term, the Laplace of the second derivative is s is second derivative, so square y, capital Y of s, right? Minus s small y of 0 minus y dot of 0 plus, so this thing is the Laplace of y dot dot plus now 2 times s capital Y of s minus small y of 0. This is of course with the same formula, the Laplace transform of y dot. And then finally, minus 15 capital Y of s is that's the transform of y equals 6 transform of the delta. Remember that we did it very easy to do with the definition, 6 e to the minus s, 8. So that is the equation of minus s 9. Right. Maybe I should write minus 9s. All right. Now this is the equation, maybe if you want, I can write this for symmetry, right? This is the equation in the Laplace domain, the S domain, okay? So we can simplify this and let's group together everything that multiplies capital Y. So if we simplify that, we get s squared plus 2s minus 15 multiplying capital Y of s. I also substitute this, where are the numbers coming from? So y of 0 in our case is minus 5, right? And y dot of 0 is 7, okay? So I substitute that and I get these numbers. Ys, right, where was I? Yeah, plus 5s plus 3. This is the most difficult one to understand with my handwriting. 5 times s plus 3 equals 6 e to the minus 9s. Although it is arithmetic, right? I substituted y0 here, this is again another minus 5. Alright. So I substituted, so this is plus 5 plus 7, so you would get, this is, no, sorry, my bad. This is plus 5s, so this one is an s. Super important that I try to make it different from the 5. So this is plus 5s, right, that you would get here. That is this 5s in here. Then you get here minus 7, and then you get plus 5 times 2, which is 10, so minus 7 plus 10, that's the 3. And the coefficients of y, you get minus 15 from this one, that's here. Then 2s from this one, that's there. And s squared from this one, so I'm just grouping. Alright, so that means I can solve for y, and that means that y of s it's equal to 6 e to the minus 9s minus 5s minus 3. So I put everything on the right hand side that is not multiplying y, and I divide by the coefficient of y, s squared plus 2s minus 15. Oh, wonderful. So now, all that we need is to find, well, what I'm gonna do, I'm gonna separate this, like these factors, right? And I'm gonna write it first like this. I'm gonna write it as 6, so, yeah, write it like that. Like 6 e to the minus 9s, to simplify it a bit, divided by, I'm gonna put this into a product of the roots, s plus 5, s minus 3. This is the most challenging problem in terms of the number of 5s and s's that appear together. So this is not 95, this is an s, right? Minus 5s plus 3, s plus 5 times s minus 3. Now, why did I write it like that? Because this looks like I'm going to get a sine and cosine, right? And this one, perhaps I would get exponentials. I'm not sure what I will get. We'll see. But looks like perhaps exponentials, and perhaps this one are sines and cosines. We don't know. We will see at the end. But at least you see that this one is going to be different. This one has an exponential. And what happens when I have an exponential? Second shift theorem. I'm going to get a heaviside. And getting a heaviside makes sense because some stupid kid kicked my oscillator after 9 seconds when I activated. Of course I'm going to get a heaviside. Suddenly the oscillator is doing its life and suddenly boom, because the kid kicked it, right? So of course there's going to be a heaviside in there. That's why I separated. When you get problems like that, always separate the exponential from the rest. Let me call this actually 6 e to the minus 9s multiplying something that I'm going to call f of s minus a g of s. And of course my f of s, let me quickly erase this here. And by definition in here, my f of s is going to be whatever multiplies this thing. So my f of s is 1 over s plus 5 multiplying s minus 3. And my g of s is going to be minus, that's important, I know I have the minus in here, so not without the minus, 5s plus 3 divided by s plus 5 multiplying s minus 3. Alright, wonderful. And then we know that to find y of t, all that I need to find is this y of t is going to be 6 times the Laplace transform inverse of e to the minus 9s f of s, right, minus the inverse Laplace transform of g of s. Alright, and why did I do that? Because now this is written exactly as in the second shift theorem, and then I know if I solve this one, I'm going to get this is equal to 6 times, and then this is theta t minus a times the f t minus a, the f, remember, so that f of t is the inverse Laplace of f of s, alright, and then g of t is the inverse Laplace of g of s. All right, so what I get here is 6 times, and then you see Laplace inverse of this one, right? I can take inverse Laplace here, kills the Laplace, and inverse Laplace here, and I get exactly this. So I substitute that expression. This is the heavy side of t minus, what's the value of the displacement? Oh, 9. So t minus 9, then small f, t minus 9, minus small g of t. Now, of course, this is what the oscillator would do on its own. This is the freaking perturbation that the kid introduced at second number 9. You see, this thing doesn't exist before t equals 9 and then start existing. Why? Because a kid came and clicked it with a lot of energy. Alright then, so all that is left to do is find f, small f of t, so f in the t domain and g in the t domain. So computing the inverse Laplace transforms of these two functions. Let's do it. So, we got the solution that was moved here. The solution is this one, right? 6 heavy side t minus 9 f of t minus 9 minus g of t, and we need to find f of t and g of t. Now we found that capital F of s is this. I do this step is simple fraction decomposition. I just did it in one step, so you have to do it yourself in a very simple fraction decomposition. Same as here, simple fraction decomposition there as well. After doing this decomposition, we need to do the inverse Laplace transform of f and g of s, so that's easy because this thing is 1 over 8 inverse Laplace of 1 over s minus 3 minus, well, the 1 over 8 multiplies the whole thing, inverse Laplace of 1 over s plus 5. And that's very simple because those are exponentials. So no sines and cosines, even though it looked like it might be sines and cosines, no sines and cosines anywhere. In principle, you never know. You can know. You actually think well about it. But in principle, you can suspect you will have exponential and sines and cosines appearing from the same kind of thing because you see, they're the same kind of thing. Anyway, whatever. So what we have here is 1 over 8 that multiplies. This would be the exponential of 3t, right? Minus the exponential of minus 5t. There we go. That's f of t. And then g of s, what we have here is the inverse Laplace of, I'm going to write it like that. I'm going to take a common factor 1 over 4, right? And this is the inverse Laplace of, so 9 times the inverse Laplace of 1 over s minus 3 plus 11 times the inverse Laplace of 1 over s plus 5. Alright, so we see that the solutions to this dynamical problem, if you want, this differential equation, it's not quite a harmonic oscillator. You can tell already because the free oscillations, that are the ones that go with G, have a positive and a negative real root, and that means that there's an exponentially divergent solution too, right? There's kind of a system that explodes. It makes sense because, you see, this comes from the elastic force, but the elastic force should be on the other side because it's m times acceleration equals all the other forces, right? Putting all the forces here. That is a friction. That is the right sign for a friction. There is friction. That's why you get also things that go down. But this is a force that instead of being the elastic force, right, that was minus kx that opposes taking it out from x equals 0, this one is larger. It's a force field that becomes stronger as you get further from equilibrium. So this thing, when you're at equilibrium, is nothing. As you move it a bit, it's and takes you really, really far away. It's an accelerator, like a particle collider kind of thing. You have a field that is stronger, actually a very, very powerful one, that is stronger the farther you are from equilibrium. So that's why you get solutions that explode, right? Again, so thinking of it as a harmonic oscillator, you would have thought immediately that that was the frequency square. What does it mean, the frequency square being negative? Indeed, it's not a harmonic oscillator because it's slightly different. It's like changing the sign of the elastic force. The farther you are from equilibrium, the more you get separated from the position of equilibrium. And in that accelerator system, suddenly you get a kid that arrives and kicks it with a driving force. You see, so that is the physical system that we're talking about here. All right. Okay, so now let's write the solution to the, I haven't written the solution to the full system, but to the full problem. Y of t, it's equal to, let me write minus g of t first. So I'll write minus 1 over 4, 9, 3e to the 3t, plus 11 e to the minus 5t, and then plus 6 times heavy side of t minus 9. You see, this thing doesn't exist until time equals 9, which is when your kicks your accelerator system. And then this function, but displaced by 9. So this is function f that I have here, 1 over 8. So this thing is 1 divided by 8. So I'm going to write here 3 divided by 4. And then I get exponential of 3t minus 9 minus e minus 5t minus 9. All right. And this is the solution to the problem. Another problem solved. All right, let's do another one, now with a heavy side. So we have here this equation is an IDT. Y of 0 equals minus 1. So starts at time 0 and position minus 1. And the velocity at 0 is going to be equal to minus 2. All right, so this system is actually really a harmonic oscillator. Look at that. So if I divide by 2, I get that the frequency square is 5. So the frequency of the oscillator is square root of 5. And you see, this oscillator is doing free oscillations. Nothing is forcing it until time equals t4. So it's doing some, move it to the right minus 1 and then push it with some speed to the left. And then it starts oscillating. We're going to see some sines and cosines. It's going to oscillate. And there's no friction, by the way, in this one. So oscillations will be there forever. And what's going to happen is that at time equals t equals 4, then your annoying kid is going to arrive and kick it with an energy of 5 to the left. So it's going to kick it to the left. So the thing is going to go, oscillating more and so on. And then at time t equals 12, there's going to be a constant force field to the right, which is of value 3. Imagine that your oscillator is charged. I activated an electric field towards the right. So the charge gets accelerated towards the right. It's biased me towards the right. That's the physics of it. So we expect some oscillations at the beginning, and then something happens at t equals 4, and then biasing after t equals 12. It's going to be cool. Let's solve it. All right. Now that we know the physics, I hope that I motivate this. With harmonic oscillators, kind of need to think about the physics, right? Accelerators, harmonic oscillators. All right. Laplace transform. Let me quickly take the Laplace transform. I am applying the usual transform of the derivative and so on. What one gets is twice s squared, capital Y s, minus s of y0 minus y dot 0 plus 10y, capital Ys, of course, sorry, equals, and then here I have to write the the Laplace transform of the heavy side. So this is 3. Okay, what is the Laplace transform of the heavy side? I have it here. T minus a is e to the a minus as divided by s. Okay, a here is 12. So this is e to the minus 12 s divided by s. And then minus the Laplace transform of the delta, well, 5 times the Laplace transform of the delta, which is just e to the minus sa. So this is e to the minus 4. Sorry, e to the, actually to the minus 4s. All right, not 45, 4s. Wonderful, I just did Laplace transform of this. Okay, so we do the usual thing. We group all the things that multiply. Well, plug in the initial conditions. So this thing, y of 0 is minus 1. This is an s, of course. Y dot of 0 is minus 2. Okay? And I plug it in, and I group all the y's together, and I get that y of s is equal to 3e to the minus 12s divided by s minus 5e to the minus 4s minus 2s minus 4 all divided by 2s squared plus 10. Yeah, you see s squared plus 10 is what multiplies y, so it goes to the denominator, everything else in the numerator. We're going to write it as follows. This is 3e to the minus 12s multiplying 1 over s 2s squared plus 10. What I did is put the s in the denominator, first term of the sum, then minus 5 times e to the minus 4s multiplying 1 over 2s squared plus 10 minus 2s plus 4 divided by 2s squared plus 10. The minus affects the 2. Alright, so I call this thing f of s, I call this thing g of s, and I call this thing h of s. Okay? Now, of course, I can do the inverse Laplace transform here, and if I do the inverse Laplace transform to get y of t, so y of t, let me write it here, maybe here I'll write it. Y of t is the inverse Laplace transform of everything, so I'm going to write it here. 3 inverse Laplace of e to the minus 12s f of s minus 5 inverse Laplace transform of e to the minus 4s g of s minus inverse Laplace of 2s plus 4 divided by 2s squared plus 10. Now, of course, that means, again, the second shift theorem tells me that this thing is going to be 3 times heavy side of t minus, well, it's the exponential is at 12 here, so minus 12, right? And then I'm going to get small f of t minus 12, okay? Then minus 5, same thing, heavy side of t minus 4, and then the small g of t minus 4, using this, okay? And then finally, minus h of t. So you see what's going on. This is the oscillatory solution of a free oscillator with those initial conditions. This is the effect of the kick that arrived and kicked it. And this is the effect of the bias that you get when you apply this constant electric field to the oscillator that is charged. How is that? It's kind of cool, I think, to understand it in physical terms as well. All right then, all that is left to do, this is the solution. I will write it here. So all that is left to do is finding f of t, g of t, and h of t. So inverse Laplace transforms to finish. Let me move this equation right there. Okay? Okay, so I move the solution there, and then I have the f, the g, and the h here prepared for me to calculate. All right, let's begin with the f. The f will be the effect of the bias. What would I expect from physics? Well, I expect that I'm displacing it from the center, so there will be a constant solution, hopefully, and then oscillations around this new equilibrium. Let's see. All right, so this thing, I already did simple fraction decomposition on it. So f of t, which is of course the inverse Laplace of f, capital F of s, it's equal to 1 over 10 inverse Laplace of 1 over s. Oh, there you go, your constant solution. Minus, so the 1 over 10 multiplies everything, right? This would be inverse Laplace of s divided by s squared plus 5. Right. This thing is the Laplace of 1, so the inverse Laplace of 1 over s is 1. So it's 1 over 10 multiplying 1 minus, and this thing is a cosine, such a clear cosine, where a is the square root of 5. So this is the cosine of square root of 5t. Now, look at that. How unsurprising is that? The frequency, remember when we talked about this on oscillator? If I divide by 2, I get a 5 here, and the frequency squared is 5, and I told you the frequency of the oscillator would be root 5. So yeah, all the oscillations in this problem go with a frequency omega of √5. Also because the frequency of free oscillations here is exactly equal to the natural frequency of the oscillator because there's no friction term. There's no term proportional to the velocity. It's kind of cool. I mean, I hope that connecting with the physics, you know, like being one with the physics. Okay? All right. It's just exciting to me. Anyway, whatever. So let's keep going. Now we do the same with the G, right? So the G I just took a factor 2 out. So G of t is the inverse Laplace of capital G of S. All right, and that thing is 1/2 inverse Laplace of, and then I get 1/s² plus 5. Same as before, but this is instead of the cosine, this is the sine, right? For this to be the sine, I need to have a square root of 5 in here. I can put it there by multiplying and dividing. So 1/2 √5 inverse Laplace of √5 s² plus 5. Now it's literally the cosine where a is √5. So this thing is 1/2 √5 sine √5t. Oh, I didn't mention it before. This one, right, has a constant term. This is the constant field energy displacing it from equilibrium constantly. The equilibrium position is being moved because of the bias applied force in it. The electric field displaces, so if your mass is oscillating here, if it's charged with electric field, it's going to displace the whole thing and then it's going to oscillate on the new one. That's what's going on. When you switch on the field at t equals 12, that's what you're going to see. Because F goes with the t equals 12. It doesn't exist before t equals 12. All right, now this one is an oscillation, and it's an oscillation induced by the kick of the kid. The kid, by kicking it, induces a new oscillation that is never dissipated. It's like a superconductor. You put a current in, the current stays forever because it doesn't dissipate. There's no friction, so the perturbation that the kid puts into the oscillator stays there forever. All right, it's not that, okay, in time it will disappear because, no, there's no friction here. The kid has left his signature there forever. All right, so now the final thing that we need to calculate is h. So h of t is the Laplace transform minus 1, so the inverse Laplace transform of s/s² plus 5. What's that going to be? Plus twice the Laplace transform of 1/s² plus 5. Right, so this is clearly the cosine again. So I get the cosine of √5t plus 2, again, I multiplied by root of, let me do it here to abbreviate. Multiply by √5, divide by √5. So I get 2 divided by √5. Now the sine of √5t. Wonderful. Let's write the solution and enjoy these final results and all the physics that we can get. Only looking at the equation, I could tell you what the solution could be. There's going to be oscillating with this frequency. And I don't know, it's kind of cool. I mean, the exact coefficients, of course, you need to calculate. But you can tell what the physics is going to be before you calculate. Okay, so now that we know what the physics is going to be, we can write the solution. And it's a long one, so y of t. So first, the one that is the bias, the displacement of the equilibrium because of the electric field that I applied, if you want. So it's 3 times f, and f is 1/10, so 3/10, okay? And I have heavy side of t minus 12, and then 1 minus the cosine of √5, and this is t minus 12, shifted. Shifted. All right. That's the part of the solution that comes because of the application of that field that displaces the equilibrium, constant force field. And you see, it kicks in at t equals 12, not before. Now, the contribution of the kid, that because there's no friction, it's going to stay forever there. It's like, again, as I said, a superconductor. You put a current in it, it stays forever. All right, so the contribution of the kid is 1/√5 2 root 5 and then multiply by 5. So this thing is minus 5. So okay, 5 divided by root 5 is root 5. So what we have here is root 5 divided by 2, minus root 5 divided by 2, then the theta t minus 4, and now the sine root 5 displays t minus 4. So this is what the kit does, and again, this oscillator has no friction, stays forever doing this. The perturbation stays forever. All right, and then finally, the H contribution here, minus, and then H is right here, minus the cosine of root 5t plus 2 root 5, oh minus, sorry, minus 2 root 5 sine of root 5t. And that's the solution. And you see, this solution has 3 components to it in a way. One, this is the free oscillations. This would have been the solution to the homogeneous problem with this initial conditions. This one comes from the bias, from the constant force field. You see, this is Newton's second law. This is the elastic force on that side, right, if you want. And then here is a constant force field, right? And the constant force field starts at T12. This kicks in at T12, this places in the equilibrium, and then the kit kicked it at times equal T4. So this is the effect of the kick of the kit that stays forever. And then the solution of the free oscillations. Notice that the frequency of oscillations is root 5, as we anticipated, no friction. The natural frequency of this is root 5. Remember, if I divide by 2, I get root 5 as the frequency, because this would be omega, 5 would be omega squared. So you can guess, looking at the equation, all the physics of the solution. Of course, you need to be practiced with it to get it, but hopefully this helps you connect the mathematical solution with what you're doing in physics. Anyway, this solves the exercise and ends the session. It's a long one. I hope that you had seen it with enough time and relaxation. I mean, drinking something nice or whatever, but or maybe seeing it in several parts. But this ends the practice session about Laplace transform, and we will come back for the topic of stability in the next video. All right? Bye-bye.